Okay, this is a recording of Chapter 1, Section 5A notes, functions and logarithms. So two of the main components of this particular section are dealing with one-to-one functions, because we can only find the inverse of one-to-one functions, and then how that relates to the fact that logarithmic functions and exponential functions are inverse operations. So they are inverse functions. So we discussed in Section 1, Chapter 1, Section 3, exponential functions, and now we're going to talk about the inverse of those particular functions. So let's just start with a one-to-one function. A function, f of x, is said to be one-to-one on a domain D if f of a cannot equal f of b whenever a is not equal to b. That can be confusing when you read that, but essentially it means this. In order to have a function, every x can only correspond to one y. To have a one-to-one function, has to be a function, so every x can only correspond to one y, but every y can only correspond to one x. And it doesn't have to be x and y, right? Any input can only correspond to one output to be a function. Be a one-to-one function, every output can only correspond to one input. So, essentially, to be a one-to-one function, the picture must pass the vertical line test as well as the horizontal line test. Writing a one-to-one function, you did this, you found inverses, writing an inverse as a function, you did this probably in Algebra 2, definitely in pre-calculus. I would switch these two. They say solve the equation for x in terms of y and then interchange x and y. Typically what we've done in the past, and I'll continue to do this because I know in pre-calculus you switched x and y and then resolve for y. Same thing. And that's probably how I'll do it because I know that's how most of you learned it last year. Base A logarithmic function. The base A logarithmic function given here, y equals log base A of x, is the inverse of the base A exponential function y equals a to the x. So every logarithmic function can be rewritten as an exponential function. They are inverse operations of each other. But what we need to know is that essentially if I want to undo the log base a, I take a raised to both sides. So a raised to the y, a raised to the log base a of x, a raised to the log base a are inverse operations, so they undo each other. Okay? And so we can rewrite it in that manner. A to the y equals x. And that is the inverse of this function. Y equals a to the x. It's really important that you know that a logarithmic function is the inverse function of an exponential function. Just like square root is the inverse of x squared. Cube root's the inverse of x cubed. Right? The inverse of the sine function is the inverse sine function. Same thing here. What's the inverse of an exponential? A logarithmic function. Here's some properties that you learned in Algebra 2. You would not have seen these in Algebra 1, but you would have seen them in Algebra 2 and then again re-emphasized in pre-calculus. Remember, log base A, it doesn't matter what the base is, as long as the argument is 1, is always 0. Remember, when we're taking the logarithm, we're finding the exponent. It actually comes from Greek word, a Greek origin, meaning exponent. So think about this. This question is really saying if the base is A, what does the exponent have to be to produce 1? Well, a to the 0 power produces 1. Where here, think of this one. Log base a of a equals 1. Don't memorize it. Think about it. If the base is a, what does the exponent have to be to produce a? The exponent has to be 1. Here, we just talked about a little bit on the previous box section. If you think of this, if the exponential function is base a, and in the exponent you have a log base a. These are inverse operations. A raised to a log base a, they are inverse operations. They undo each other. So we just end up with the argument x. Similarly, if I take log base a of a to the x, these are inverse operations. So it just produces the x. Okay? So these are properties of logarithms that we need to know. But more importantly, these three are going to pop up frequently. So the product rule for logarithms. These are not calculus rules. It's just product rule for logarithms. And the product rule simply says, if I'm taking the log to any base of a product, I can take the log of that base of the first factor plus the log of that base to the second factor. So if I'm adding logarithms, I can make it one logarithm and multiply the arguments. Or if I'm taking the logarithm of a product in the argument, I can separate it into two separate logarithms. Sometimes we want to take this side and smash it together, as Mr. Hearn would say. And other times we want to have this and we want to be able to expand it out. It just depends on the context of the problem. Likewise here with the quotient rule. Log base A of a factor divided by a factor. So a quotient is the log of the numerator minus the log of the denominator, using whatever this base happens to be. And again, 90% of the time, please understand that in calculus, we're going to be dealing with natural logs. Power rule. The power rule says this, and we've already used it some in the chapter, in the section 3 problems that we've done. Log base A of an argument raised to an exponent, that exponent can drop down and become the coefficient of this logarithm. In other words, the exponent drops down out in front of the logarithm. We use this one frequently. And you can prove this if you were to set this equal to something and take A raised to both sides, you can prove this. But essentially, we use it so much, it's really something that we should know. The log of an argument raised to an exponent, the exponent drops down out in front of the logarithm. And then probably one of the most important in calculus is this one, the change of base. Because all this logarithmic stuff is great, but we're going to convert everything to a natural log. And we're going to do it this way. The logarithm of any base of an argument is always the natural log of the argument over the natural log of the base. In algebra 2, a lot of times you use the same by just saying log and log. We always want to convert to a natural log in calculus because we're only going to remember one rule for derivatives and integrals, and that's the rule for the natural log. Okay, we'll convert everything to a natural log as we proceed into the more calculus-oriented topics. Example number 1. On these problems, I just want you to determine whether the function has an inverse or not. In order for it to have an inverse, it must be a one-to-one function. Can we switch x and y and resolve for y? This one you can, and we're going to look at some of these, some rationals. So I'm not going to go through finding the inverse. We'll have some examples where we will. Okay? But essentially, on some of these, you would have to think about it graphically. It has a vertical asymptote, it has a horizontal asymptote, but it is a one-to-one function. We could take a look at it in the calculator and graph it, and we would see that this is an always increasing or always decreasing function. That's the key to telling whether a function is an inverse function or not. Is it always increasing or always decreasing? So a lot of times these rational equations will have inverses. On this one, this cubic function, cubics can be a little bit confusing because sometimes they have inverses and other times they don't. On this particular situation, it does not have an inverse because this cubic turns. Let's just take a look at this one in the calculator. It's easy enough to type in x cubed minus 4x plus 6. Y equals x cubed minus 4x plus 6. Okay, and hit enter. I like to always hit a zoom, not graph, because I don't know what the particular zoom is at this point. I'm always going to start with either a zoom, zoom 6 for zoom standard, or zoom 4 is even better for zoom decimal. Let's see what zoom 4 tells us. Zoom 4, here it is. We see that this turns right here, and maybe a zoom 6 would be better, zoom standard. We see that we have two turning points. This does not pass the horizontal line test. Therefore, this does not have an inverse. This particular problem here, I wish that they would have just given me y equals the natural log of x, because that does have an inverse. But then when I square the x, it does not. Let's just look at it real quickly in the calculator again. The natural log of x definitely has an inverse function. When we look, I'll go zoom 6. Zoom 6 is just 10 by 10. It looks like this graph stops here, by the way. The calculator can be misleading. If I go zoom 4, I'll see a little bit better maybe. But I could keep zooming. This is going to get closer and closer and closer to this vertical asymptote we'll find when we graph these functions. But it is an always increasing function. And since it's an always increasing function, it does have an inverse. But if I do this, if I go back here and I insert, or I hit my squared key and then close it, and we graph this function, now it's no longer a one-to-one function, right? And you can see how this approaches the asymptote a little bit better in this function. It's no longer one-to-one. It does not pass the horizontal line test. It is a function, still a function. That's why this is no. This one we should know, this is a parabola opening upward. Parabolas opening upward, they're not one-to-one functions. This cubic can be difficult because if you switch x and y, you really don't have a great way to isolate y to verify that you have an inverse, but it does have an inverse. If I graph x cubed plus 4x, y equals, clear this, x, math 3, that's how I do x cubed, plus 4x. And if I graph it, this is a cubic function that does not turn. And that happens sometimes, particularly when you don't have a squared term. So if it's x cubed plus 4x, for instance. Okay? So this is yes, although we would struggle to find the inverse here. So we'll have other ways to deal with the derivative of this inverse later on when we get into calculus. Exponential functions typically have inverses, just like logarithmic functions do. We can graph this 3 raised to the 2 minus x. Let's just take a look since we've done this. Y equals, clear this out, 3 raised to 2 subtract x. Now make sure your cursor to the right so we're done. And if I graph this, there it is. Okay? You might want to look at a zoom 6 to go 10 by 10. All right? And we can see that this is an always decreasing function. Since it's an always decreasing function, it has an inverse. Right? Just real quickly, remember on this, we graph some of these. The horizontal asymptote here is y equals 0. We could see that. Okay? And it does go up forever. So identifying whether we have an inverse or not is important, but it's not going to be critical as we progress. These problems are going to be on the first test where I ask you to find the inverse of a function. I also want you to graph this because I want you to recognize that a function and its inverse, when you graph them, are mirror images about the line y equals x. And also, after we're done finding the inverse, notice it says verify that they are indeed inverses by checking these composites. This is the part you're not going to like. Some of these composites can be tricky, but to me it's the most important part, that you're getting used to how these composites crank out. Because recognizing compositions, particularly compositions that are inverses, is important. Let's just start with how you learn this. I rewrote this function using y and x. I switched x and y. And again, I know I'm going through this fairly quickly. So if you're watching this, you may have to pause it to write down the work. And now I want to resolve for y. I subtract 3, divide both sides by 2. I have isolated y. Once I isolate y, I call that f to the negative 1 of x. That's how I denote the inverse function, is x minus 3 over 2. But it wants me to show these composites, and this is frustrating for some students. It's important that you go through the process and not just copy the work, because the ones that are on the test, it's easy for me to tell if you're actually cranking through the composites or just trying to do what I call fake it, because you already know what the answer is. The nice part about these problems, you already should know what the answer is. So let's do f of f negative 1 of x. I've written it right here. F of f negative 1 of x. It says take x, plug it into the f inverse function. Here's the f inverse function. When x comes in, x minus 3 over 2 comes out. So I can replace this f negative 1 of x, the inverse function of f, with x minus 3 over 2. But now that output is the new input into the f machine. The f machine says take 2 times whatever comes in and add 3 to it. 2 times this came in, I'm going to add 3 to it. I can cancel the factors of 2, and now x minus 3 plus 3, the negative 3 and the positive 3 cancel to be x. One of the cardinal rules throughout the year will be this rule right here. I just call it rule number 1. So if you see a point deduction and it says R1, R1 stands for this. Never cancel terms and factors in the same step. So I will see students that cancel here and then cancel the negative 3 and the positive 3 all in the same step. We cannot do that because I don't know if you know how this is being processed. The 2's are being canceled first in this composite, and then the negative 3 and the positive 3. These are terms, these are factors. Sometimes you cancel the factors first and then the terms, and sometimes vice versa, like this. Now I have to crank it out the other way. F negative 1 of f of x. Well, take x, plug it into the f function. This comes out. That is the new input into my inverse function. The inverse function says take the input, subtract 3 from it, and divide by 2. Here's the input. Subtract 3, divide by 2. Notice now the terms cancel first. That's why I don't want to cancel terms and factors in the same step. Then the factors cancel to produce an x. It's knowing how this is being processed that's important, not the final answer. They're telling you the final answer. You're verifying it. So you have to show separate steps to show the process. And since we did get x back out, I want you to write the summary statement every time on the test and quizzes. And the directions will say, write a summary statement, because much of the AP test is about writing quality conclusions using appropriate mathematical terminology. And we're going to start with something easy because really you're just repeating what the directions said. You're going to say, since this is true, right? So since f of f negative 1 of x equals f negative 1 of f of x equals x, comma, the functions are inverses. Don't say they are inverses. No pronouns ever when we are giving an explanation for anything mathematically. We will not use pronouns, particularly it. Do not use the word it. All right, let's take a look at another one. A nice cubic function, because a lot of cubics are one-to-one functions. Let's say we didn't even recognize if it was one-to-one. Let's just try to find the inverse. Here it is. Write it using x and y, switch x and y, and resolve for y. Add 1. How do I undo y cubed? I take the cube root of both sides. Y equals the cube root of x plus 1. Now just think about it. It seems to make sense, right? If I plug something into this function, I'm going to cube it and then subtract 1. So it would make sense that the inverse would be add 1, the inverse of subtracting 1, and then take the cube root. It's just the same functions in opposite order, the opposite functions in opposite order. But let's check. We want to check these composites. So I like checking this direction first. F of f negative 1 of x. Take x, plug it into the inverse. This comes out. The cube root of x plus 1 is the new input into the f function. The f function says take whatever comes in and cube it. Well, if I cube this cube root, they're inverse operations. So it eliminates the radical symbol. X plus 1 minus 1. Now the plus 1 and the minus 1 cancel to produce an x. Where if I do it this direction, f negative 1 of f of x, now x goes into the f machine first. X cubed minus 1 comes out. And x cubed minus 1 goes into the inverse machine. Whatever comes in, add 1 to it first, then take the cube root. So here I'm canceling the terms first. And then I'm taking the cube root of x cubed. That should be an x cubed right there. I forgot to write down my cube symbol on this. That should be the cube root of x cubed there. Okay, so make sure that you notice that. I'm going to go to this real quick and show you, here's the step, should be the cube root of x cubed. Make sure you write that down. Those undo each other, and I get x. Okay. So let's go back to the actual document now. Since f negative 1 of f of x equals f negative 1 of f of x, let me say that again. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. This statement you're going to want to write every time. The directions will say that on tests and quizzes. I graph these two for you, plotting some points. Here is the cubic function. Here is the cube root function, and you can plot some points. They're pretty easy to graph. I dotted in the line y equals x, so you can see that they are mirror images about the line y equals x. Remember, we have to have a cube right here, okay, on that x. Okay, two more of these, and then you can work on some of these inverse functions. So what do we do with functions that are not entirely one-to-one, like 1 over x squared? If you graph this in your calculator, you're going to find it's not a one-to-one function. It does not pass the horizontal line test. So we restrict the domain. We're going to define this function only when x is greater than 0. So y equals 1 over x squared. That, we can find the inverse of it because we're only looking at the right-hand side, which is a one-to-one piece. Switch the x and the y. In order to resolve for y on some of these rationals, sometimes students struggle. If you have a y in the denominator, you need to multiply both sides of the equation by that denominator so we can get y up on level ground. In this case, I just switched the y squared and the x, because it's the same thing as multiplying both sides by y squared and then dividing both sides by x produces this. To solve for y, I need to take the square root of both sides. I need to consider plus or minus, but that would not be a function. I need to decide, do I want positive or negative values for y? Well, if I plug in only positive values for x, that means I should get out only positive values for y. X and y are switching roles. So I only want positive values for y. I want the positive piece. If this was x is less than 0, the work would be exactly the same, except I would have the negative. I would keep the negative sign. Let's check our composites. Take x, plug it into the inverse function. 1 over the square root of x comes out. That goes into the f function. The f function says, take the input. Here's the input. It's coming right here for x. I'm going to square it, take 1 over that. So it comes right in here. Look at my circle. 1 over the square root of x squared. 1 squared is 1. The square root of x squared is x. And 1 over x, take the reciprocal, is x. Let's check the other direction. Take x, plug it into the f function. This comes out. Here it is. Now the inverse function says whatever comes in, here's my inverse function right here. Whatever comes in, take the square root of it, and then take the reciprocal of it. So if 1 over x squared comes in right here, it's 1 over the square root of 1 over x squared. The square root of 1 is 1. The square root of x squared is x. Take the reciprocal, we get x. I graphed both of these for you. Although this one is kind of hard to see because they look real similar, they are a little bit different in how quickly they approach the x-axis and the y-axis. So they are slightly different. You could look at them in your calculator and blow it up a little bit if you wanted to, but you need to make this summary statement. It's the same every time. If f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. And we have to get used to being able to state these conclusions. There's going to be more writing on the AP test than you probably have done in any of your previous mathematics classes. And part of it is just getting used to writing correctly using mathematical notation. That's why I'm having you do this. You're probably not going to have to write this particular statement, but you're going to write statements very similar to this that involve calculus notation. Last one is the hardest. I have put this on tests and quizzes before, not because it's the hardest, but because I think it forces you to utilize more algebra. And that's going to be the key, is how strong you are with your algebra skills. This is a one-to-one function. You could put it in your calculator and see. One thing I would notice, look at the vertical asymptote here is x equals negative 3. And the horizontal asymptote here is y equals 2. That means in our inverse, those two should switch. So if my horizontal asymptote is y equals 2 for the original function, the vertical asymptote should be x equals 2. If my vertical asymptote in the original function is x equals negative 3, my horizontal asymptote in the inverse function should be y equals negative 3, because x and y are just switching. That's what we're doing right here. We rewrite the function using x and y, and we switch x and y. As soon as we do this, x and y have just switched responsibilities. They've switched roles. But a lot of students, due to fractional notation, struggle with getting y by itself. You have to practice this type. It will be on a test or quiz. Again, I'm solving for a variable in the denominator, so I have to multiply both sides of this equation by the denominator. In this case, it's the same thing as cross multiplying, right? The denominator here is 1, so I don't have to multiply that up, but multiply the x plus 3 to the other side. Don't forget parentheses. A lot of times students who are not detailed in their work will write this without the parentheses and then forget to distribute. I need to distribute so that now I have 4 separate terms. But oftentimes students will forget the x here. Okay? So now I still have an issue. How am I going to get y by itself? I have 2 terms involving y. If you have more than one term involving the variable that you're solving for, you have to get all of those terms on one side and all of the terms not involving that variable on the other. So I subtract the 2y from both sides to get that 2y over with the x times y, and I subtract both sides by this 3x to get that term away from the variable for which I'm trying to solve for, in this case, y. How do I make 2 y's become 1? That's why all these terms have to involve a y, because I can factor out what is commonly referred to as the greatest common factor. I can factor a y out of both of those terms. Don't forget your parentheses. And now, in order to solve for y, I just divide both sides by this binomial factor, x minus 2. And now I have isolated y. Before you proceed with doing the composites, let's refer back to what we talked to about the asymptotes for this inverse function that we have now found. The vertical asymptote here was x equals negative 3. Look at the horizontal asymptote, degree on top is same as degree on the bottom, is y equals negative 3. Yeah, x and y just switched roles. Here, the horizontal asymptote was y equals 2. Degree on top, same as degree on the bottom. So look at the coefficients of the highest degree terms, 2 over 1, y equals 2. Should be the vertical asymptote here. Yep. What makes this denominator equal 0? 2, x equals 2. So we are pretty sure that these are inverse operations. But we still have to crank out the composites. And this is the hardest part, but to me is the most important part. I think over the years, One concept that has given students difficulty in calculus is rational functions, just working with complex fractions. So we are going to practice them early and often. We have to be able to simplify complex situations. So if I take x and plug it into my inverse function, it's right here. This comes out right here. But now this is the new input into my f function. Think about this. 1 minus 3x over x minus 2. That fraction has to go in for x right here and right here, both of those spots. Here it is. I write it like this. Again, use parentheses. Here's the key. Simplifying complex fractions. Worked on in Algebra 2, talked about it in pre-calculus. You'll hear me say this a lot. Use Mr. Hearn's method. Many times, teachers will start with saying, oh, get a common denominator here. Multiply by x minus 2 over x minus 2. Multiply by x minus 2 over x minus 2. Make this all one fraction. Make this all one fraction. Then multiply by the reciprocal. Yikes. That's a lot of writing and a lot more work than you should have to do at this stage now in your mathematical experience. What I say is, what is the lowest common denominator considering all of these denominators? What's only x minus 2? X minus 2 is the lowest common denominator. So let's just multiply everything by x minus 2. Look at, if I multiply this, there are 4 terms here. 1, 2, 3, 4. If I multiply every term by x minus 2, a factor of x minus 2, look at the x minus 2 just cancels here. And I'm left with 2 times 1 minus 3x. I wrote it right there. But I've got to multiply this by x minus 2. If I multiply this fraction, this term, by x minus 2, the factors of x minus 2 cancel. I'm just left with 1 minus 3x. But I have to multiply the 3 by x minus 2. So instead of getting this all to be one fraction and this all to be one fraction, then dividing by these big fractions, we can eliminate the complex fraction by multiplying top and bottom by the lowest common denominator, and you can eliminate it in one step. It's going to save you significant amount of work, and I think it's easier to do. Now I'm going to distribute the 2. I'm going to distribute the 3. I'm going to write all these terms, and again, never cancel terms and factors in the same step. Cancel the 2 with the negative 2. I add these 2 terms together and get negative 5x. Cancel the negative 3x and the positive 3x. 1 minus 6 is negative 5. Now I can cancel the factor of negative 5, and this says x here, by the way. Cut off a little bit, okay, but that's an x. We got out what we were supposed to get out. Now we got to do it the other way. It's a lot of work, I know. So take 2x plus 1. Take x, plug it into the f function. If x goes into the f function, where's my f function? Here it is. X comes in, 2x plus 1 over x plus 3 comes out. This is the new input into my inverse function. This is my inverse function right here. But this input has to go in here and here. That's what creates the complex fraction. So if I plug 2x plus 1 over x plus 3 in for x both here and here, here's what we get out. I'm going to do the same thing. I'm going to go from complex to non-complex in one step, always in this class. If you want to make this all one fraction and all one fraction multiply by the reciprocal and show 2 or 3 additional steps, I'm okay with that. That's fine. But I'm trying to make you get used to writing as consistently or as quickly as you can, as concisely as you can, to save you time when it comes to the AP test. And this is a skill, this complex fraction, that if you just practice it, it will get better. I only have one denominator in top, and it's x plus 3. I just have to multiply each term by x plus 3. This is a term. All of this is a term. I'm subtracting the 2 terms. This fraction is a term, and that 2 is a term. I'm subtracting. I multiply each term by that denominator. 1 times x plus 3 is just x plus 3. And if I multiply this term by x plus 3, the x plus 3's just cancel. But I cannot forget the parentheses. Parentheses make a significant difference. Multiply this fraction by x plus 3. Just cancel the x plus 3. Multiply this negative 2 by x plus 3. Look at complex to non-complex in one step. It's the way to go. Distribute the negative 3. Don't forget to distribute the negative sign. Distribute the negative 2. Don't forget to distribute the negative sign. Now I can cancel 3 and negative 3. 1 minus 6 is negative 5. I can cancel the 2x and the negative 2x. 1 minus 6 is negative 5. In most problems, the last step is different. This one, they happen to be the same. But I can tell by the second to last step if you crank them both out or if you just tried to make it look like you did. Okay? So cancel the negative 5, you get x. Write the summary statement. Since f of f negative 1 of x equals f negative 1 of f of x equals x, then the functions are inverses. Okay? I graphed these two just so you can see some rational functions being graphed. Let's just start with this one here, 2x plus 1 over x plus 3, that function. Notice, remember, it had a horizontal asymptote of y equals 2 and a vertical asymptote of x equals negative 3. So there's the vertical asymptote. There's the horizontal asymptote. I'm graphing this picture, okay, right here. Where this one that's a little bit darker, that is the inverse function. Remember the inverse function, 1 minus 3x over x minus 2. It has a vertical asymptote at x equals 2 and a horizontal asymptote at y equals negative 3. So it looks like this. It's the darker one. And I dot that in. They are mirror images. It's a little bit more confusing to see this because there's a lot going on in these graphs. If you are still struggle a little bit with graphing these rational functions, don't worry too much in chapter 1. You're not going to have to graph it on a test in chapter 1 because we're going to graph enough of those in chapter 2. We'll graph plenty of the rational situations in chapter 2. But I just wanted to show it to you just to get the idea of how these rational functions are working. Okay? Here's the assignment. Those are the notes for 1.5a. These anytime I put challenge problems, if there are students who don't feel that they're challenged enough by some of the problems that I assign, these are problems that extend it a little bit. You don't really have to know it for the A/B test, but they're good problems for you to look at if you want to challenge yourself and try a few more complex problems. You can certainly try the challenge problems. They are not on the worksheet. Okay? Just these problems that are listed here will be on the worksheet.